So population growth, exponential models. We looked at situations like the Ebola outbreak and cities changing in population. Suppose a city has a population of 20,000 people. And based on the recent Census Bureau, we think that that population is growing by 3.5% per year. Now, a situation like this is basically a yearly compound interest problem. And our formula for that is the future amount is equal to the present amount times 1 plus r to the power t. That's our formula right there. So if I enter this information in here, then the future amount for the city is going to be equal to 20,000, their starting population, times 1 plus this number as a decimal. Let's see, double check, 3.5%. Percent means divide by 100. If you divide by 100, that's going to shift the decimal point twice and give you 0.035. So that's going to give me 1.035 to the power t, and t here is going to be years. Now I can clean that up. 1 plus 0.035 is 1.035. So the equation for this city's population is 20,000 times 1.035 to the power t. What are these numbers again? This number here is the starting population. This number here, the growth rate is hidden in there. The 1 is whatever the current year's population is. The 0.035 is the growth rate. So 0.035 is the actual rate of growth, which is really 3.5%. So looking at this equation right here, I can say, hey, this city is growing by 3.5%, right? That's how I got there. If I wanted to then predict a future population for the city, that's what this A is all about here. So maybe I want to know how many years is it going to take for this city at this rate to get up to like 25,000? So then I would just have to solve the equation. Given my starting point, 20,000 times 1.035 to the power t, I want to know when is that equal to 25,000? And we've solved equations like this before. We divide by 20,000, divide by 20,000. Yep, got enough zeros. Here I have a number divided by itself is 1. On the other side, I can reduce a little. And do you have to reduce it? The answer is no, but sometimes it's nice. Divide by 1,000 top and bottom. I could call it 25 over 20. You could reduce it more. I'm just going to leave it there. That's okay. Just a little less ink is nice. And then we do our logarithms. Log of 1.035 to the t equals the log of 25 over 20. If you reduce that further, that's cool. The t pops out. And then I would divide to finish this off. T is connected by this multiple, so I divide by it to get rid of it. And hopefully we're getting used to that step. It's something new this week. Now this side right here is a number divided by itself. That's gone, that's a 1. 1 times t is t. The other side, nothing cancels. The logs are stuck. We just have to plug this into a calculator and then check. So a reminder about how to plug that in and check. So we think Desmos is a great calculator for this. Maybe you have a handheld calculator that's great. Don't use the straight Apple calculator, that one sucks. So here I have the log of 25 over 20, close the parentheses in the right spot, then divide by the log of the base. My base was 1.035, close parentheses. So this tells me around 6.5 years later. How do I know that's true? I could have screwed this up. Go back to the original equation. The original equation said take a population, starting population of 20,000. Looks right. My base was, so times the base, mine was 0.35, 3.5% increase per year, raised to the power, and I think the power is about 6.5, so I'm just going to type 6.5. And yeah, that's about 25,000. So I got it right. So I solved it, I checked it, had used logarithms to solve it. So then I would report back to the city council and say, hey, if we continue, this city continues to grow at 3.5% per year, then in 6.5 years from now, our population would be about 25,000 people, right? And cities need to plan for these kinds of things, infrastructure, schools, right? This is important stuff, planning for the future. Hope you found that helpful.